Start the recording. So welcome to everyone for the weekly seminar at the LMFL. Today, the seminar will be about, the title of the seminar is Enhancing Numerical Weather Forecasting with Generative AI Model. And it will be given by Gabriel Moldovan, which is a postdoctoral researcher at the Centre National de Recherche Météorologique within the ANR POESY project. It focuses on artificial intelligence application for numerical weather forecasting. So Gabriel earned his PhD in fluid mechanics from ISAE and TMA in 2022 under Professor Marcello Meldi's guidance. The PhD was concentrating on developing a sequential data simulation strategy for intricate unsteady flows. During his doctoral tenure, he pioneered an innovative data simulation algorithm which blends together the multi-grid approach and ensemble Kalman filter. So this approach significantly slashes computational costs in sequential filtering methods. And then, motivated by his work in data simulation and a profound fascination with numerical simulation and data-driven techniques, Gabriel Moldovan transitioned into the domain of artificial intelligence for numerical weather prediction. So he recognizes the ongoing revolution in weather forecasting sparked by deep learning models. So looking forward, Gabriel is keen on exploring how AI methods can not only advance numerical weather forecasting, but also tackle broader scientific challenges. So Gabriel, I will let you start the seminar if you're willing to.
Hello everyone, yes, of course. Let me try to share the screen.
Yeah.
Well, I cannot share it.
Oh, wait a second.
Before that, I'd like to say hi.
Yeah, we tested it.
So it works now?
It should.
Let me see that. Do you see the screen now?
Yeah, I do.
Okay. Let me share. Okay, so I think you should see my my presentation. If
I'm seeing it, and
okay, perfect.
I
Well,
can
I'd
hear
like to
clearly.
start by saying thanks for inviting me here. It's really an honor, and also like to say hello to, I've seen Marcello and Luca and Miguel that are connected. So I know Miguel and Luca from my PhD era, and Marcello was my supervisor. So it's very nice to see them. So yeah, I'd like to thank Marcello and also Francesco and Paolo for the invitation today. So yeah, I will give a brief overview of our research activities in the use of generative models for enriching and enhancing atmospheric ensemble forecasts. So of course, this is a collaborative work mainly performed by Laure Raynaud, which is the coordinator of our project, Clément Brochet, which is a PhD student here at Météo-France, myself, and also other contributors such as Basile Guindon, Louis Poulain, Julien Rabot, and Cyril Reguin, which have worked with us on the development of this strategy. So what will be the plan for this talk? I'll start with a brief introduction, then I'll move on to explaining what we are doing with generative models in an unconditional manner, then on a conditional setup, and then I'll finish with some conclusions. Well, first of all, what is ensemble forecasting? The atmosphere is probably the greatest example of a chaotic and complex system. So forecasting the state of the atmosphere is an inherently uncertain procedure. Multiple errors may be coming from initial condition, boundary conditions, and model errors as well. So instead of relying on a single simulation, forecasters use an input, a variety of input in order to produce multiple possible outcomes. So what we are doing is that we are using ensemble forecasting in order to characterize the uncertainty in the actual forecast. Now, the model that we are focusing on is the limited area model centered over metropolitan France, high resolution with a grid size of 1.3 kilometers. This might be funny for some of you to see high resolution with a grid size of 1.3, but in meteorological studies, this is really the case. And for this model, the AROME ensemble prediction system, we have a very constraining operational limit that limits actually the number of ensemble members that we might use to 16. And this is not enough to properly characterize forecast PDFs. Now, in the context that I've presented, and also in the context of the ANR POESY project led by Laure Raynaud, my supervisor, we are asking the following question. Well, can we use the generative models such as GANs, the generative adversarial networks, and diffusion models to produce AROME-like forecast, conditions on the ensemble forecast of the day, and enrich these ensembles by adding multiple AI-generated forecasts to it in order to better characterize the forecast PDF. This might have a significant impact on the assessment of, example, extreme weather events that may be on the tail of the distribution and that might be harder to detect. I'd also like to give a broader view on the actual state of AI in numerical weather forecast, because in the last year, there's been a real revolution around it. So what has happened is that from the beginning of 2022, there have been multiple papers in Science, in Nature, you might have seen them, of big tech companies that have used basically an enormous and high quality reanalysis data of the state of the atmosphere in order to train emulators for models for numerical weather forecast. And what's really interesting about this is that they are claiming to beat the best model that we have today, which is detained by the ECMWF, which is the European Center for Weather Forecasting. And this poses significant challenges to traditional weather forecasting centers, because with AI, we can be much faster, and these big tech companies are claiming to be even much more accurate. So the question that we may ask is, well, in 10, 20 years, will traditional weather forecasting methods completely die? This is still to be seen, but there's quite a revolution going on in this field. So let's go back to, to our project. The first step that we have explored is, well, can we use generative models to emulate the diversity and detail of an AROME forecast? So let's see if we can use generative models to produce outputs that are physically accurate and with the good correlations in them. Now, let's talk a bit about the dataset. So in AI, the dataset is essential, primordial. So we have 517 daily AROME ensemble forecasts over southern and center of France. So the domain is depicted here. So we have the Pyrénées, the Massif Central, la Vallée de Rhône, et les Alpes. Et ici on a, and here we have the Mediterranean Sea. We have split this dataset in train, validation, and test, as we usually do in AI studies. So we have 1.5 years of data. We have 16 members, and we have simulations up to 45 hours with a delta T of 3 hours. So what we'll try to do is that we'll generate 3 variables in a multivariate fashion. So we are looking at the first component of the wind vector at 10 meters, the second component of the wind vector at 10 meters also, and the temperature at 10 meters. So this is 2D, these are 2D variables. And basically the output that we want to generate will be 256 times 256 resolution output with 3 channels, each channel for the variables that, for each variable that we are looking at. Now, what is a generative adversarial network? Let me try to explain it briefly with an example here. So GANs are deep learning models with two identities. So we have a generator and a discriminator. Imagine the generator as a counterfeiter and the discriminator as the police. So the objective of the generator will be to print fake money, and the objective of the discriminator will be to distinguish between fake and real money. And the thing here is that the generator never actually sees how real money looks, but it's just through the feedback of the generator that he manages to actually improve his qualities to generate more and more real money. So basically, both are trained. The generator is trained to fool the discriminator, and the discriminator is trained to catch the tricks of the generator. And the competition happens, and the magic happens through competition. So at some point, if things are done right, you have a generator that is so much skilled that the discriminator will not be able to distinguish between fake and real money. Mathematically, this can be explained through this loss. I won't go into detail because we could speak maybe 1 hour or even days about the mathematics behind GANs, and they are still not well understood. But what I've said now can be basically explained through this loss here. So it's a standard min-max loss. And both identities in the deep learning model will be trained against this loss here. The discriminator will want to maximize this loss, while the generator will want to minimize it. Now, we have explored two types of GANs. In the traditional setup, what we want to do is to take a Gaussian noise. We want to learn basically a mapping from this Gaussian space into the pixel space, or in physics, into the physical space. So basically, this is the whole thing that we are doing here. As you can see in traditional ones, we are just feeding this Gaussian noise to the first layer, and then this signal is transformed, upscaled, and modulated in order to obtain the physical space. In more state-of-the-art architectures, what we'll do is that we'll first introduce an intermediate latent space. So basically, we are taking our Gaussian noise, we are transforming it to this intermediate latent space. And then instead of feeding it to only the first layer, we are actually introducing to multiple layers across multiple resolutions inside the architecture of the generator. And this allows for a better control of the generation capabilities of the generator. Now, we can take a look at the actual StyleGAN generator. So StyleGAN is the model that we have chosen to work with. So you can see that it's quite complex, composed of multiple convolutional blocks, but maybe 2 or 3 ideas to get from here. So we have here the input noise. This input noise is passed through fully connected layers in order to have a latent code, in the latent space. And then basically our output is constructed from a fixed image or a fixed block here that we have. So in this fixed block, we have images or fields of 4x4 in terms of resolution with 512 channels. So progressively, this field here is upscaled and modulated in order to add more and more information to it through this latent code. As you can see here, this information is injected at multiple layers. And in the end, we have an output that is on the physical space or on the pixel space that we're looking at. Now, there's also noise injection in the process. So this is Gaussian noise that is injected in order to encourage stochastic variation. And this may have, for those who are expert in the field, you can maybe recognize the residual structure. And there's many gradient regularization techniques that are used here that I won't go into detail, that help actually the generator be able to print this fake money that is really indistinguishable from the real one in terms of the example that I gave before. Now, if we take a look at the discriminator, basically what he does is that he takes the image generated by the generator and also real images, so that they might have a given resolution with a given number of channels, and we progressively downsample these images, and then up to a point where up to a final fully connected layer, what we get as an output is a critic score. So with this critic score, the discriminator will determine whether this sample that we are giving to him is real or fake. So this architecture is a bit more simple than the one that I presented to you before. When compared to the generator, it's clearly also inspired by residual networks. We have different techniques such as mini-batch standard deviation in order to increase the variation in the generation. And also there are a lot of variance control techniques in order to make it work, but I won't go into detail. So basically here is an example of a randomly generated sample. So to explain it again, basically what we are doing is that we are giving samples to the GAN basically, and we are asking him to learn the distribution that is behind them. So from a Gaussian noise, we are asking the generator to map this noise into the physical space and to produce an output that is physically coherent and with good correlations. And here we can see that basically the outputs of the GAN are actually pretty good. So we have shown this to forecasters, and also we have metrics to compare well, whether the generation is accurate or not. And well, it does actually produce pretty accurate physical fields, as you can see here, apart from them being visually quite beautiful, I would say. And if you take a look at how what is actually happening inside the generator, well, you can, in this StyleGAN architecture, you can take a look at the intermediate outputs of the generator. So you can see that the physical field starts with a resolution of 4x4, and then it is progressively upsampled, and details are progressively added, let's say, to the image. And after all this progressive and gradual procedure, at the end, what we have is the final image on the physical space. There is another generative model that we have explored, but in less detail. We are just starting to explore this type of models. I would say that this is really what the models that are à la mode, let's say, because GANs have been used up to 2021, and then when diffusion models started to be discovered, everybody started to basically do research on them, because it's also the reasons are not quite well understood why one or why the other, but research has shown that you can get better results with denoising diffusion models in some given setups. So in diffusion models, there are basically two types of models that we can explore. So there's the denoising diffusion probabilistic models, and there is the latent diffusion models. In DDPMs, basically what you do is that you start from an image in the pixel space, and you use the diffusion process to gradually add noise to this image. So you noise it. After some steps, basically you have just Gaussian noise. And what you do after that is that you learn with a deep learning model, you learn the reverse procedure in order to go backwards. And this can be quite powerful, as I will show to you. The problem that we have with these models is that they work on the pixel space or the physical space, and they can be quite expensive. So here come latent diffusion models, where what we do is that we use an autoencoder to basically project the pixel space onto a latent space, which is of lower dimension, where basically in this vector hill, what we have is we have the essential features of the physical field in the physical space, and this allows to be much more efficient in terms of the application of the denoising diffusion probabilistic model. So we do the same as we did here, but in the latent space. And all these new image generation models that you might have heard about, DALE and Stable Diffusion, are actually working on this kind of models. Now, so a quick reminder, as I said, what we have trained these models in the unconditional generation setup is to take a random noise and then to generate a random field from the actual data set. What is important to notice here is that the generator in this case has never seen any sample from the real data set. So what it's trying to do is to actually emulate this data set without having never seen any image from the actual database. So what we can do is, well, we can take 20,000, for example, random noises and then produce 20,000 random physical fields and see if the distributions that we obtain are actually similar to the ones that we might obtain in the original dataset. For that, we'll need some kind of metric. And well, I won't go into the detail because this comes from optimal transport theory, and I'm really not an expert in this field. So what we can use is the Wasserstein distance, or also called the Earth mover distance. So the Earth mover distance basically characterizes the discrepancy between two distributions. And why do we call it Earth mover distance? Well, because we can imagine two distributions, and if we want to characterize the discrepancy between them, we can consider them to be piles of soil. And the distance between them, what we'll say is that is the amount of soil that we'll need to move times the distance that this quantity will need to be moved in order to make the two of them actually identical. So we can calculate this Wasserstein distance in the pixel-wise in the univariate case and in a very simple manner, but this is not enough. We want to have also texture metrics, but we can do this by actually projecting the physical scale on coarser fields, and also calculate this Wasserstein distance in a more complex manner, but this gives a texture information that we can then compare in terms of differences of distribution. Now, let's see an example here. So this is a pixel on the physical field that we obtained. So for the same pixel, we are looking at its distribution for multiple samples. And here you can see that, well, a bad grid point would have a typical Wasserstein distance of 32 times to the power of -3, while a good grid point, meaning that the distribution seen on this grid point, would have the Wasserstein distance of the order of 5 to 6. So here you can get a rule of thumb of what would be good results in this case. So for the evaluation of unconditional generation capabilities, we can also look at multivariate distribution. And here in color, what you have is the multivariate distribution that we obtain from the dataset, from the actual dataset. And in black and white is the distribution or the contours that we obtain from the GANs. And you can see that they're actually very similar. So this shows that the distributions that we obtained with GANs are actually very similar to the ones that we have in the dataset. So we can also check more numerical scores. So for example, here we have the texture metric score, the slice Wasserstein distance, and also we have the pixel-wise. And you can see that the scores are quite good. So here I'm showing the results for StyleGAN, DDPMs, and latent diffusion. You can see that basically DDPM, the diffusion models kind of beat GAN in every aspect, but on the very fine scale. And the latent diffusion, well, it's the results are good, but are not quite as good as the ones that we obtain with StyleGAN or DDPMs. Now, as I've shown you, well, we can train GANs and diffusion models to accurately emulate very complex physical fields. But what we want to do is not exactly that. What we want to do is to take an ensemble forecast and then use a GAN in order to enrich this forecast. So basically, what we want to do is to attain conditional generation, not unconditional one. So can the generation of forecast be conditioned to a given AROME ensemble forecast? This was basically the second step of our research activities. And basically, there are many ways to attack this problem, but we have chosen to work on the latent space. As I have introduced previously, you can basically in the style GAN architecture, the Gaussian noise is actually projected, transformed into an intermediate latent space. And this latent space actually has very good properties that we can exploit, as I will show you. So given an input forecast, basically we can use a trained generator in order to obtain, well, the latent code that best represents the input field. So basically what we are doing here is we are giving the generator a real forecast, and I actually asking him to produce the latent code that will best represent it. So we do it with a stochastic gradient descent, as I show you here. So basically, this latent code is composed of, in this case, 12 to 14 vectors that will contain the information or the, let's say, the essential features of the physical field that we are inverting. Now, here you can see an example of an inversion to the latent space. So basically, this is the input, and we are doing here either 200 to 1,000 inversion steps in order to obtain the latent code that best represents it. And well, as you can see, the more inversions we do, the better the accuracy is in the actual inversion. This is quite expensive, so we cannot use an infinite number of inversions. So we have to be, how to say, we have to keep a good balance in this procedure. Now, once we have this latent code that best represents the input forecast, what we can do is that we can propose a conditional generation of forecasts in the latent space in a three-step procedure. So we'll take the AROME ensemble, so the model ensemble that we have in the physical space. We will invert it to the latent space, and then we will produce new latent codes from the latent codes that we have obtained from the inversion. By simply perturbating them, we'll apply control perturbation to given parts of the latent codes obtained in order to generate new ensembles. And then we just pass them through the generator in the inverse sense in order to obtain an enriched ensemble in the physical space. Basically, this is a very simple three-step procedure. When we actually take a closer look at what is actually happening inside the perturbation in the latent space, so we have two degrees of freedom. We can choose what kind of perturbation we use in this latent space, and also what parts of the latent code we are actually perturbating. So concerning the perturbation method, we can either use random perturbations, we can use interpolation, extrapolation in the latent space, or we can either use a PCA resampling, for example, for getting the principal directions in the latent space that are important and that the directions that give variability. Concerning the choice of the style vectors or the parts of the latent code that should be perturbed, well, we can use an optimization procedure for that. So a priori, it's hard to say which one should be perturbed, but we can actually learn which ones of them should be perturbed in order to obtain the good characteristics of the ensemble. So here is an example of a forecast generated via PCA resampling. So in this case, all the entire latent code is perturbated. So you can see that we have some variability here in the generated forecasts, but this variability is controlled. It's not random variability. Why? Well, because we have efficiently managed to condition this generation to a state, to an input state, which fixes actually which part of the generation is changed or not. So it seems to work. Let's see if it really does. In terms of conditional generation for diffusion models, for us, this is still a work in progress, but there are two strategies that are being explored. So first, I would like to check if we can condition by directly guiding the denoising procedure with a target. So basically, the denoising procedure is an iterative procedure in which the noisy latent vector is passed through the model multiple times. So we can basically control this denoising procedure with a target in order to give directions to the denoising. And also, we would like to emulate the work of Li et al. This is a paper from NVIDIA from some months ago, where basically they have implemented a conditional training framework in their diffusion model, where basically they split the ensemble in two, and they take some members that they give to the diffusion model, and they ask the diffusion model to produce the other members. And this can be quite powerful in order to condition actually the generation to not the climate of the dataset that we're exploring, but to the actual distribution of the ensemble forecast. So this is still work in progress for us. Here is an example of guided denoising. So here's the target, and here is the input physical field. And depending on the guidance that we use, and on the forcing the amount of guiding that we want, we get an output that is either closer to the input or to the target, as you can see here. So this is some ideas that we could use in order to produce conditional generation with diffusion models that we are still exploring, of course. Now, we have seen that there are some strategies that we can use in order to condition this generation to a given ensemble forecast. But now we need to see if these enriched ensembles actually outperform the traditional ensemble in terms of traditional scoring rules. So here I'll talk about continuous ranking probabilistic score, spread skill, rank histograms. I think it would be also interesting for you because I discovered this kind of scoring rules here in the weather field, numerical weather field, and I think they're quite powerful for currently analyzing ensembles. So concerning the continuous ranked probability score, so basically I think it's better explained with a figure. So we have here the cumulative probability distribution, and here we have a Heaviside function. Sorry, this is for the ensemble, and here we have a Heaviside function for the observation. So basically what you are calculating with the CRPS is the area defined by this function here that you have. I'm hearing someone, so could you please mute your microphone? Thanks. And another relationship that we can take a look at is the ensemble spread error relationship. I won't go into detail because this can be quite mathematical, but intuitively I think
Oh, I'm sorry, Gabriel. I'm just trying to mute everyone, and then I can unmute you. Sorry. Okay. Can you unmute yourself?
Do you hear me?
Yeah, I can hear you now.
Okay.
Sorry.
So going back to CRPS, CRPS is just the equivalent of the maximum average error that you have for the deterministic forecasts. So the smaller it is, the better, basically. Going back to the ensemble spread error relationship, it is also, I think, intuitive to get here that in an ensemble, the error of the average of the mean of the ensemble to the observation should be of the same order as the spread of the ensemble. So this is a relationship that weather forecasters will actually analyze when analyzing ensemble prediction systems and seeing if spread and error are of the same order, basically. Now, let's take a look at some results. So here I'm presenting to you four different tests for the test database. So we have used the GAN. Here it's only for GANs. I used the GAN to enrich a database that has never been seen by the discriminator or the generator. So here the comparison, let's say that it's fair. So I'm presenting to you here four different tests. In black, you have basically the original AROME ensemble prediction system. And here I'm showing you the continuous rank probabilistic score. And basically, as I said, is the equivalent of the mean average error. Now, what I was saying, yeah, so in black, it's AROME. In green, it's a test where the perturbation is obtained from PCA. And all the parts of the latent code are perturbed. In blue, it's a test where the ensemble has been enriched with random perturbations, and the parts of the latent code that are perturbed have been obtained from optimization. And the same has been done for this final test, where the perturbations are obtained from PCA, but we also use optimization in order to obtain what parts of the latent code should be perturbed. And basically, you can see here that for the module of the wind speed, the CRPS is lower actually than the one we obtained in the original ensemble. So this is very good news for us, because it means that basically we really managed to enrich the ensemble by using our AI model. For temperature, you can see that we also managed to decrease the CRPS, but the improvement is less significant, I would say, than the one that we have for the module of the wind speed. Here you have spread and skill plots. So skill is basically the root mean square error, or an equivalent metric to the root mean square error. So as I said before, we should have skill and spread that are of the same order. And you can see that AROME, the original AROME EPS system is greatly, the spread that we have in it is too small compared to the skill, so they should be of the same order. But when we use the ensembles enriched with the generative models, we see that we actually have a bigger spread. So basically, what we gain by using generative models is that we increase the variability in the ensembles, and this has a positive impact on the actual evaluation metrics that we use for ensemble forecast. I would also like to show another type of evaluation metrics. Here we have histograms. So rank histograms, sorry. So what we'll do is that we'll take the entire test dataset with the enriched ensembles, and each ensemble will order it, we'll sort it from small to big values, and then we'll see where the observation falls within this range. And if we do this with all the ensembles, at the end, if the ensembles are well equilibrated, we should have a uniform distribution. You can see that in the AROME case, this is of course not the case. This is typical of our underspread of an ensemble with not enough spread, basically, because we have a lot of overliners here. A lot of times the observation is just outside the ensemble and is not actually captured by the ensemble prediction system. When we use the generative models to enrich the ensembles, we can see that actually the number of outliers is reduced by a lot, and we kind of move towards a more uniform distribution, but we are still not quite there, but there's still an improvement in the rank histograms that we obtain. Here is basically a very interesting case, because here you can still see that the ensembles for wind speed are there's still not enough spread in them, because we have this typical distribution. But in this case, you can see that for temperature, some of the tests that we have performed, there is too much spread. So this is kind of one of the problems that we have right now that we need to solve, is that when we use conditional generation in the multivariate setup, we get much more spread for temperature than for the other two variables, and this is really a problem for us that we are trying to solve. So here, the observation falls too much in the middle of the ensemble, meaning that the spread is just too high, and we have ensembles that have just too much variability. And the final evaluation score that I'd like to show you are reliability diagrams. So the same as I said before, so we take the full data set. Here we are taking, of course, the test data set. And here we have to define thresholds. So for the wind speed, we have defined a 5 meters per second threshold and a 10 meter per second threshold. And for temperature, 278 and 288. So what we want to do here is that we want to check if whether every time that the AROME forecast predicts, for example, a 50% chance of exceeding this threshold, we want to see if the actual observation happened in the same frequency. Because if you have an ensemble prediction system that gives too many false alarms, it will not be reliable. So it's better to follow. The ideal case here would be to have a line that is perfectly diagonal in this sense. So you can see here that there are reliability issues with the original AROME ensemble, but with the enriched GANs, we managed to be closer to the perfect case that we have here. And basically, we can also see that for temperature, we also managed to basically increase the reliability of the ensemble prediction system. So I think I move on to the conclusion, because I speak on for a lot of time. So generative models excel at retrieving the target around APS distribution they've been trained against. So we have seen the metrics that we have obtained for unconditional generation. DDPMs or diffusion models seem to narrowly outperform StyleGAN in all unconditional metrics, but on the ones concerning very fine scales. So on the bigger scales, they seem to be better than StyleGAN, but StyleGAN is still better in the very fine aspects of the physical fields. So we have seen that enriched ensembles outperform the original AROME ensemble prediction system in terms of observation scores. So this is quite good, and we are really happy about this. But there are still some concerns about the computational cost, especially because of the inversion to the latent space. And while we are still trying to explore the conditioning strategies identified for diffusion models, which are promising, but we still need to work on that. So as a perspective, I would say that we're also working on the exploration of other variables, such as precipitation, which is quite more difficult because it is an intermediate variable. So you may have fields full of zeros, and then at some point in your field, you might have some information about the rain. But it's much more difficult than fields such as temperature or Gaussian or wind, which are more continuous, and in distribution they are also very similar to the Gaussian distribution. Also, we're working on optimizing the inversion procedure, so to reduce costs, and as I said, to continue with the exploration of conditioning strategies for diffusion models. So yes, this is still ongoing work, and I hope you have found it interesting, and I'll be happy to answer any question that you may have about this work. So thank you.
So thank you very much, Gabriel, for the really nice and intense, I would say, presentation. And I will open the question for the public. So I see some hands raised already in chat. So please, you're free to unmute yourself and ask your question. Okay, Marcello has one.
Yes, can I start then? Because I had not my hand raised when you said that, so I was like, okay, I'm gonna wait a second. Thank you, Gabriel, for this very nice talk. I'm so happy to see that you're working on very, very interesting subjects. I have a double question, if I may, and I'm gonna ask it at the same time. So actually, the first part deals a bit with the presentation that you did. I think it was a wee bit before halfway, in which you started explaining the real application of the GAN, and you compared it with the diffusive model and the autoencoder based model, right? It felt to me that in different way, these approaches are kind of like multi-level. Because when you were showing the GAN, you started with elements that were 4 times 4, and you got more and more refined. And so my first question is it possible to perhaps apply the strategies that you developed for DA for multi-grid and multi-level in a sort of with a strong coupling to these techniques? And after that, the question number 2, which may be somehow connected, this generative model show a very high potential for these flows, but I mean the flows that you represent in meteorology do not have the complexity of the flows, you know, that we usually analyze in fluid mechanics, in terms of recirculation regions, von Karman Street, Kelvin-Helmholtz instabilities. Is it going to be that easy also to develop generative models for fluid mechanics, or do you think it's going to be more complicated, and why? And now I shut up.
Am I still muted or?
No, we can hear you.
Okay, so for the first question, they are multi-level in the sense that, for example, GANs, in style GAN, especially, the image is generated progressively, but it's true that I fail to see like a direct application of data simulation, because usually the problem that you have with AI models is that there are black boxes, and you cannot really understand what's happening inside. But what the application that I really see with GANs, and this I will show I will share the screen again. Sorry, is there is an application on data simulation, and I just like to share. Yes, autorize. Do you still see me or my screen? So
yes.
basically in the inversion step, where it is here, this is basically, if you check the loss function, this is for the var, because you have, imagine, for example, you train, this is like an ideal setup. You train a data set. You have a data set with, for example, velocity fields, and you train, let's say it's a data set with turbulence or whatever, and then you have observation or sparse observation of a given field. What you could do is use an inversion procedure where the target is just this sparse field, and the GAN will actually give you a full field that is actually in accordance with the observation that you have given to it. So I think that for flow reconstruction, GANs can have a lot of potential, and I've also discussed about this with many colleagues, and there's a lot of people that want to try this. But I think for flow reconstruction, this can be quite interesting. And for the second part, it's true. Yes, I've always thought about this, because the problem that we have is that we're using 2D fields, but probably in the future, this will AI and generative models will also be used in, I don't know, for example, in turbulence, or in cases where you have databases of LOS simulations in very specific applications. You might be able to learn specific parts of a flow, and then use this to generate or to reconstruct flow. I think there might be some applications to make fluid mechanics, but of course there is an issue concerning computational expenses that is there, and it won't go away very easily.
Okay, thank you very much.
Are there any other questions from the public? Please feel free to unmute yourself and ask your question.
Hi, can you hear me?
Yes.
Yeah, we can hear you.
Yeah, great talk. Thank you very much. GANs are notoriously difficult to train. I saw you had lots of regularization techniques. Was there any other kind of methods that you used to kind of get convergence when training your GAN?
So thank you for this very nice question, because basically, yes, when you read papers on the fusion models, this is always that the argument that you always read is like, yeah, GANs are very hard to train. It's very hard to train it, but I have to say that we've had a very different experience from that. So basically, we found this model, and we used a style GAN model that we found on GitHub from a researcher, from a developer that was interested in style GANs, and we just changed the data loader. I don't know if you're a bit familiar with artificial intelligence, but we just trained it with fields of 3 channels. Well, let's say friendly fields, I would say, and then the results were there. So we really didn't have to change much about the architecture or anything. Like the GAN was really accurate from the start, and I think it's really a characteristic of style GAN. If you give him fields that are more or less well behaved, I would say, you can have very good results without much work. So this is quite it was quite impressive for us to see that in the end, when we actually compared diffusion models and style GAN, and we had much more issues with diffusion models than we actually did with GANs. So I would say that we didn't actually develop or implement some crazy regularizations terms in order to make it work. We just used what the paper said, or we just used the model that the paper gave, and we had very good results from the start. So maybe we are the exception, but I really think that GANs can be very, very skilled in doing in recovering distributions from complex data sets.
Interesting. Thank you.
Any other question? Okay, Gabriel, if you want, I have one. So I'm really I'm not an expert of GANs as you do, but I was wondering how many hyperparameters are out there when you deal with GANs that you have somehow to if you have to tweak, or if you have to tweak some, how many hyperparameters actually to make it works correctly.
So basically, if you the amount of parameters that they are in the model in conditional sense, it's millions. But hyperparameters, I would say that it's quite robust. So we didn't do much tests on learning rate on that. We use really the parameters, the hyperparameters that were recommended by the paper where we got the style GAN from. And from the start, we had very good results. We didn't spend a lot of time trying to tweak and twist the architecture in order to make it work. So in terms of that, we are quite happy with it. And then with the procedure that we have developed, there are some hyperparameters, I would say, concerning the conditioning of the generation. But if you follow like a very strict method, you can still use some optimization procedures to make it work, I would say. So it's it's nothing crazy. Like I think we could easily use the conditioning strategy that we have developed on any other ensemble prediction system that might exist.
So basically, there's nothing to be optimized to maintain like a good balance in between generated sample quality and training stability.
Actually, yeah, it's the training stability. It's very robust to changes in hyperparameters. Like we did some tests on changing like the learning rate or the size of the latent space or some internal parameters of the architecture, but it still manages like it has a very robust architecture. Like I didn't say it, but the Stargate was developed by NVIDIA, so you have to imagine 20 big heads working at the same time with immense computational power. So it's quite a robust thing. I have to be honest. And I also have to say, like for those working in AI, maybe they know it, but the community power that we have in AI is quite amazing because you can have very powerful codes, and there's this open source how to say atmosphere, so everybody shares its code, so it's really easy to find in GitHub the code that you want, or the model that you want to try, and then you can easily adapt it, and they're well coded, and this I really appreciate this kind of approaches that we have.
So that's surprising because normally NVIDIA, I was not thinking that the NVIDIA was willing to share their code. So
basically, yeah, they do. Right now, there is really this politic. I don't understand why they do it, because it's true that they don't win money or anything from doing this, but probably it's to encourage development in the community, and it's quite powerful, I would say. This really encourages people to use the codes and produce interesting solutions. So it's really a part of the community that I really like about.
I see. And then one last question is more about computational cost. So you have been saying that sometimes it can be really intensive computationally. So do you have an order of idea of, I mean, an order of magnitude of how many GPU hours or CPU hours you have
So
been consuming?
basically for training, so I would say that for example in the test, the GAN that we have trained, we have used a data set of 300,000 samples, and on one GPU we still managed to train it on a resolution of 256, which is not very big, but it's okay. And we have used probably around 100 to 150 hours of training on a single GPU, and I think it's quite correct. Like when you check what they have done, for example, in the papers that I've showed you at the beginning, where they have trained the model emulators on 512 TPU for months, so it's not the same order of magnitude.
Yeah.
So I would say that we are using the orders of we're using computational powers that are still okay, not doing some ecological disaster or something. No, let's say it's okay. We didn't use a lot of GPUs for the trainings that we have performed.
Okay, thank you very much for the answer. And besides, I imagine that all these GPU applications are naturally. I mean, I do know some sort that normally neural networks, at least, or but I don't know if it is if it is the case for GANs, they are naturally parallelizable. Like you can use the GPU power in order to accelerate somehow the training.
Yeah, basically what we do here, it's a kind of an easy parallelization, is that since we are training on batches of images or batches of physical fields, we are using batch parallelization. So we've used a batch of 32, for example. We'll take 4 images times, or 4 GPU times 8 time. Sorry. So we take 4 trainings with a batch size of 8, and then we'll use that in order to produce a global training of a batch size of 32. So it's how we parallelize actually the training. Then it's quite simple, and the framework. So basically, we use Python. I didn't say this, with PyTorch, and it's very easy to parallelize, and it's really nice to work. To not work with MPI.
Okay, thank you very much for your answer, Gabriel. The presentation
Thank
has
you.
been really nice. I don't know if there is someone in the meantime think about some question they want to pose. Well, as Francesco says every time, it does not seem to be the case. So I will tell you goodbye, Gabriel, and thank you again for the really nice presentation. And
Thank you for the
say
invitation.
everyone, and I say hello to everyone. So rather goodbye to everyone, and see you on the next seminar.
Okay,
Bye.
thank you, everyone.
Bye-bye. Thank you, Gabriel. Bye-bye, everybody.
Ciao.